I'm going to walk you through solubility rules and how to do net ionic equations in this video. Knowing when something is soluble or insoluble is very important here. So these solubility rules that you're going to see, you need to know them, okay? If you remember back when we were talking about reactions and double replacement reactions, we said that sometimes double replacement reactions don't happen. It's all based on these solubility rules, okay? So now we're at the point where we need to know these solubility rules so we can determine if a double replacement reaction actually happens. So the first four rules are dealing with when things are soluble with some exceptions here. Okay. And maybe it's important to point out here if something is soluble, okay, that means it's going to be aqueous. So you have to remember this. If something is soluble, that means when you put it in water, it's going to be AQ or aqueous. It's going to dissolve. So if you were writing a reaction, you would label it as AQ in parentheses. Now you need to worry about if things are aqueous or solid here. If something is insoluble, that means it's not going to dissolve in water, so it would stay as a solid. You would see solid in parentheses after the substance. That's very important here. So you can read these rules, but you do need to know them. The first one is talking about salts of ammonium or alkali metal compounds always being soluble. So if you have a compound that has ammonium in it, NH4, automatically you know it's always going to be aqueous or soluble. And same thing for those alkali metals, the far left column. As soon as you see an alkali metal in a compound, you automatically know it's always going to be soluble. Rule 2 says chlorides, bromides, and iodides are usually going to be soluble or aqueous, except when they have silver, mercury, or lead with them. Then they would be insoluble. So if you had silver chloride or lead chloride, that would be insoluble. It would stay as a solid. It would not dissolve in water. Okay, but all the other chlorides, bromides, and iodides would dissolve. Rule 3 is saying that chlorates, so ClO3 compounds, acetates, C2H3O2 compounds, and nitrates, NO3 compounds, are all soluble. Okay, so anytime you see, NO3 in a compound, a nitrate, you automatically know it's going to dissolve, it's going to be aqueous. We call this rule the CANS rule, okay? Chlorates, acetates, nitrates. And then rule 4 is talking about sulfates, so SO4 compounds. So again, you need to know your polyatomics here. These are always going to be soluble, except when you have calcium, strontium, or barium sulfate, or again, the silver, mercury, and lead, which we saw in rule 2. So if you had silver sulfate or calcium sulfate, that would be a solid. If you tried to put it in water, it would stay as a solid. It would be insoluble, but all the other sulfates are going to be soluble here. So you do need to know these rules and you need to know these exceptions. So the first four here are usually dealing with when things are soluble with exceptions for insoluble. The last three rules are going to deal with when things are insoluble with exceptions for soluble here. So rule 5 says that phosphates, so PO4 compounds, carbonates, CO3 compounds, and sulfides, watch the ending here. So those are things with sulfur in them, okay? They're always going to be insoluble. So they would always be solid. If you put them in water, they're not going to dissolve, except ammonium or alkali metal compounds. Basically, you can't have like a rule like rule 5 breaking rule 1. Okay, so if you remember, rule 1 said that all ammonium and alkali metal compounds are soluble. So these rules work together here. All right, so typically phosphates, carbonates, and sulfides are going to be insoluble, except if you have ammonium with them or one of those alkali metals in the far left column. They're always going to be soluble. Rule 6 says all metallic oxides are insoluble. Basically, what that means is anytime you have a metal with oxygen, all right, they're going to be solids. If you put them in water, they're not going to dissolve. Again, except ammonium and alkali metal compounds, rule 1, they have to be soluble. And then rule 7 is dealing with hydroxides, OH compounds. They're typically going to be insoluble as well, except ammonium and alkali metal compounds, again, rule 1, and it says group 2A from calcium down. Basically, it's the calcium, strontium, and barium again. All right. So in this rule, calcium, strontium, and barium hydroxide would all be soluble. It's kind of different from the sulfate rule. All right. So be careful with these and definitely look these over. So again, Now, when you look at an example here, you are responsible for including whether or not things are aqueous or solid here based on your solubility rules. So if you look at the first compound here, magnesium nitrate, this follows the Cahn's rule. All right, nitrates are always going to be aqueous, so it's labeled as soluble. It would dissolve in water. NaOH is labeled as aqueous because Na, okay, that's rule one. It's an alkali metal in the far left column on the table, so it's automatically going to be aqueous. And you could even get this with rule 7 too. I mean, hydroxides are typically solids, except ammonium and alkali metal compounds, and then calcium, strontium, barium as well. So the rules all work together here. But notice when this reaction takes place, you get magnesium hydroxide here, and that's going to be a solid. Again, that hydroxide rule says that hydroxides are typically insoluble or solids, except ammonium or alkali metal compounds. Well, magnesium's not ammonium. He's not an alkali metal. He's in the alkaline earth metals. And then it says from calcium down. So calcium, strontium, or barium. He's neither of them. So he follows the rule. He's going to be solid. And then the NaNO3 here, that's labeled as aqueous because of rule 1. Okay, it's an alkali metal, or the nitrate rule, rule 3, because it's a nitrate, right? So this double replacement reaction would happen because you got a solid forming. If you didn't get a solid forming, okay, a precipitate forming, the double replacement reaction would not happen. You need to study these rules and you need to know them inside and out. So if we do a little practice here, we just want to label each of these as soluble or insoluble, okay? So you definitely need to look at your solubility rules and figure this out. And eventually you got to get to a point where you know those solubility rules and can just look at something and know if it's soluble or insoluble. Okay, so remember here, if something's soluble, okay, that means it would dissolve in water. You'd see AQ in parentheses after it. If it's insoluble, that means it doesn't dissolve. It stays a solid. So you would see the S in parentheses after it. Okay, so if I were you, I would pause the video, try these, and then come back and see what you got here. All right, so the first one, sodium carbonate, that's going to be soluble, okay, because sodium, all right away, sodium, Na, is in the far left column. Alkali metal, rule 1, says it's automatically going to be soluble. When you get to the next one, lead sulfate, this is going to be insoluble, okay? Sulfates are typically soluble, all right, but then not calcium, strontium, barium sulfate, or silver, mercury, or lead sulfate. All right, so it follows the rules here. The next one, barium nitrate, is going to be soluble. All right, nitrate, all right, the Cahn's rule, nitrates are always automatically going to be soluble or aqueous. Ammonium phosphate, automatically going to be soluble. Ammonium compounds, rule 1, are always soluble, always dissolve in water. And then cobalt 2 hydroxide here is going to be insoluble. All right, hydroxides are typically solids, except ammonium or alkali metals. Well, cobalt's not ammonium. It's not an alkali metal. It's a transition metal. Or calcium, strontium, or barium. He's neither of those, so he follows the rule. He would be insoluble. So definitely know these solubility rules. Now we're going to see how you can use these solubility rules to do something called net ionic equation. Okay, net ionic equations are when you're only showing the ions that are directly involved in the chemical reaction. So you're kind of getting rid of any of the extra stuff here. You would only do a net ionic equation if you're told to do a net ionic equation. Okay, so you wouldn't do this all the time. It basically takes equation writing and goes a little bit further with these solubility rules. So before we do this, there's something here called spectator ions that you need to be familiar with. All right, these are ions that would be on both sides of the equation, so they cancel out. All right, because they're the same on both sides. They're not directly involved in the overall reaction, so they cancel out. So when we're doing one of these examples, we'll look at some of these spectator ions. So here's basic steps for writing a net ionic equation. The first thing, you need the balanced equation. So you know you need to be good with writing and balancing equations, maybe predicting products here. You need to still do that, all right? But then you would rewrite the equation showing the ions that form in solution for anybody that's soluble. So you will need to use solubility rules here in your balanced equation. All right, anybody who's soluble or aqueous is going to have to turn into their ions, and we'll see what that looks like. All right, Any spectator ions then would cancel out on both sides. If all of them cancel, you actually have no reaction taking place. The reaction itself would not happen, all right? But you still have to show everything canceling out. And then the last thing you do is just rewrite what's left, and you'll have your net ionic equation. Again, you're only doing this if it says to do the net ionic equation. So let's just jump in and do an example here. So for this reaction, you can see it's completely written and balanced already, and all of the solubilities are already in there. So don't think that every net ionic equation is going to be like that. You might have to go through and write the reactants and predict the products and then balance it, and then knowing your solubility rules here to be able to do the aqueous or solid. But if you look here, you can see that we are using those solubility rules. So for lead to nitrate, nitrates are always aqueous. Potassium iodide, potassium is an alkali metal, so it's always aqueous here or soluble. But this lead to iodide is listed as solid because remember, chlorides, bromides, and iodides are usually soluble or aqueous, except silver, mercury, or lead. Okay, so that's going to be a solid. And then for the last one here, it's listed as aqueous or soluble because you have either the alkali metal rule 1 or the nitrate from rule 3. All right, so that's already done for us. All right, so we wrote the equation, we balanced it, we indicated the solubility. So because we're doing a net ionic equation, we got to go a little bit further here now. Okay, so what we're going to do is, once you have your equation written and balanced, it's important to make sure it's balanced here with your solubility, you now look at every compound individually. So for this first one, the lead to nitrate, I see that's aqueous. Anybody who's aqueous, what that means is if you put it in water, it's going to rip apart into its ions. Remember, all right, ionic compounds here are going to dissociate in water. So if lead to nitrate in water, it's not actually lead to nitrate. It's going to rip apart into its ions. Remember, ions have charges. So when you put lead to nitrate in water, it's going to turn into Pb2 plus, because that's the first ion here. That's going to be your cation, plus 2 of the NO3 minuses. Very important to realize here that according to this formula, there's got to be 2 of the NO3 minuses for every 1 of the Pb2 plus. Okay? So the reason we're doing that is because it's aqueous. When you put it in water, it's going to dissociate and rip apart into its ions. All right. Next one, Ki is also aqueous, so it's going to rip apart into its plus and minus. So it's going to turn into 2K plus 2I minus. Notice when you balance the equation and you put your coefficient in front, that carries through for both of these here. Then when you get to your PbI2, it's listed as solid. So when you put that in water, it does not dissociate. It does not dissolve. So it stays as PbI2, and you must include the solid to indicate that that's why it's not dissociating. All right? And then we have the 2KNO3. It's aqueous, so it's going to rip apart into its ions. 2K plus 2NO3 minus here. Okay? So you ripped apart all of your aqueous substances and turned them into their ions. The solid stays together. Now we're looking for spectator ions. All right, those that are the same on both sides of the equation that are basically not important here for the overall net ionic equation. So I can immediately see that K plus is the same on both sides. There's 2K plus on both sides. So he's gone. That would be a spectator. All right, and then I can also see that there's 2NO3 minus here on both sides. So that's gone. That's a spectator. If I asked you, if I gave you this reaction and I said, what are the spectator ions? You would tell me K plus and NO3 minus. Okay? So the spectator ions are gone. So now you're ready to write what's left. So we got Pb2 plus 2I minus going to PbI2 solid. This would be your final answer here. All right, and that would be your net ionic equation for this. Typically, it's already balanced. If you balanced it, sometimes you might have to simplify it, so you just got to watch. But this would be your answer for this problem, and you do need to indicate the solid here in parentheses because that's what's saying why that didn't dissociate. So that's a pretty basic example of a net ionic equation. We're going to try another example here. So for this one, they gave us the
reactants, and they told us whether they're aqueous or solid. So they went through and used the solubility rules. So we have to predict the products here. All right, so the first thing I have to do is I have to look at the reactants and figure out what type of reaction this is going to be. So I see that the first substance is a compound. The second substance is a compound. So this is going to be a double replacement reaction. Okay, so that tells me, all right, what my products are going to be here. The K is going to essentially stay. Its new friend is going to be the Cl. When you do symbols, charges, crisscross, it's going to be KCl. And then you do have to indicate if it's aqueous or solid here. So when you do this, all right, you'll quickly see that it's going to be aqueous because of rule 1. Potassium is an alkali metal, far left column, so always aqueous. Then the calcium's new friend is going to be the CO3. So when you do symbols, charges, crisscross, the 2 plus on the Ca, the 2 minus on the CO3 cancel. So it's just going to be CaCO3, and that's going to be solid, all right? Carbonates here are typically solids. Remember, phosphates, carbonates, and sulfides are typically solids or insoluble, except ammonium or alkali metal compounds. Calcium is not ammonium, and it's not an alkali metal, so it follows the rules, okay? So now you have your products predicted here. You have to go through and balance. So it looks like I'm going to need a 2 in front of the KCl, and then it looks like everything else is balanced here. All right, so now I'm ready to go through and work on the net ionic part here. Again, you would only do this because it's telling you to do a net ionic equation. So anybody who's aqueous would dissociate in water. These are ionic compounds, so they have to rip apart into their ions. So I see that the K2CO3 is aqueous, rips apart. It's going to be 2K plus CO3, 2 minus here. All right, aqueous for the CaCl2. So you're going to have Ca2 plus 2Cl minus going to, okay, KCl is aqueous. So we got 2K plus 2Cl minus here. Remember, anybody who's aqueous rips apart into their plus and minus ions. Pay attention to the amounts. But the CaCO3 is solid, so it's going to stay as a solid. It's not going to rip apart. All right, so now we're looking for any spectators. I see the K plus is the same on both sides, so he's gone. The Cl minus are the same on both sides, so that one's gone. And then I write what's left. So I have CO3, 2 minus, plus Ca2 plus, going to CaCO3 solid. All right, so that would be the net ionic equation for this particular reaction. It's only showing the substances that are involved in the actual reaction. So there's one more example here we're going to try. All right, again, we were given the reactants already with the solubility indicated. Don't always count on that happening. You might have to do your symbols, charges, crisscross to write out the reactants and then predict what forms. But again, we have to figure out what type of reaction this is going to be. We have a compound reacting with a compound, so that's going to be double replacement here. All right, so that tells me that, they're going to have 2 things switching. So barium's going to get a new friend on the product side. So when the barium joins up with the chlorine and you do symbols, charges, crisscross, it's going to be BaCl2, and that's going to be aqueous. Chlorides are typically aqueous or soluble, except silver, mercury, or lead. Well, barium's neither of those. Plus, we got Na joining up with the NO3. When you symbols, charges, crisscross, they're both 1 plus 1 minus. So it's going to be NaNO3, and that's going to be aqueous here. All right, because of rule 1, alkali metal always aqueous, or the nitrates always being aqueous. All right, so don't forget we have to balance this. Some people get so excited because, they're doing the problem that they forget to balance. Sometimes I do that, so you have to be careful. Looks like we need a 2 in front of the NaCl, and then a 2 in front of the NaNO3, and then that should make it balanced here. All right, so anybody who's aqueous now, you got to rip apart into their ions. So it looks like I got Ba2 plus 2NO3 minus plus 2Na plus 2Cl minus going to Ba2 plus 2Cl minus plus 2Na plus 2NO3 minus. Okay, they were all aqueous here, so anybody who's aqueous rips apart into their ions. So now you're looking for spectators, anybody who's the same on both sides. Well, I see 2Na plus on both sides. I see 2NO3 minus on both sides. I see 2Cl minus on both sides. And I see a Ba2 plus on both sides. So if you notice, everything canceled out. So this would be listed as a no reaction. RXN stands for no reaction. And you do show your work, show everything canceling here. But again, the reason why this didn't happen is because you didn't get the solid forming. You didn't get a precipitate in your products here. All right, so you should immediately know that this would not be a reaction. If you actually mix these substances, this double replacement reaction would not happen.